Last three topics from Unit 2. If some of you remember the Unit 2 test and all of the math we did, percent composition of a hydrate, calculating an empirical formula, calculating a molecular formula, some of that is just too long for a comprehensive final. I'd rather ask you the questions in a little bit different of a way than having you solve a ton of math problems. There are a few you'll have to do. You will need to know how to calculate a formula mass from last time's review, and a percent composition for a problem that doesn't have a whole lot of participants in the compound. For something that only has like 2 elements hanging out, percent composition is easy. And we're going to start off reviewing percent composition. 2 big steps in calculating percent composition. First one, calculate the formula mass. Second one, divide each individual mass by the total times 100. If you remember and you want to do this, go for it, but I'm going to do the one from your packet, the one that's in the notes right here with aluminum chloride as an example. If you remember, there were some of them in your packet, I think we did acetaminophen or Tylenol, where there were 4 different elements in the compound. 4 different calculations. For a final, I could give you one with 2 because it's quicker. And that's what I'm looking at, is not to have you at your final all day. So for percent composition of AlCl3, first thing I need to see is that it's 1 aluminum and it's 3 chlorines. So from the periodic table, my masses, my molar masses in grams, 26.982 for aluminum. And for chlorine, it's going to be 3 times its mass, 35.453 grams. If I multiply that by 3, and of course I'm reaching for the trusty calculator, 3 times 35.453, I get 106.359 grams. So I said my first step was to get my formula mass. I'm going to add that plus 26.982, and I get, for my total, 133.341 grams for my total mass. All right, great. When I get my formula mass, I'm almost done, believe it or not. So what I need to do now is figure out what percent of aluminum chloride is aluminum and what percent is chlorine by mass. So I take the mass of each. For aluminum, 26. Actually, we'll do that. We'll say for aluminum, I think you guys can still see, yeah. It'll be 26.982, my mass of aluminum, divided by my total, 133.341. Make sure I do times 100, because that's the way a percent works. And if I do that, it looks like I get, and we'll double check, 26.982 divided by 133.341 times 100 gives me 20 point, let's go 1 digit after the decimal. You could do more, 20.2% aluminum. At this point, I see if that's about 20, I know they got to add up to 100, so I bet my other one is right around 80. Let's see. For chlorine, I need 106.359 divided by 133.341. Like I said, I think I know, but I'm going to double check. 106.359 divided by 133.341 times 100. I got 79.8%. If I add those two up, they add up to 100. That's great. Sometimes because of rounding, you might get 99.9 or 100.01, and that's fine. I know that those are very close to right, if not exactly on, just because of the rounding, because they add up to 100. So aluminum and chlorine, that's percent composition. Not too bad. You have a practice on that coming up at the end. And I think that's our last actual math like that. You're going to subtract a little, but we should be good. The next topic is empirical and molecular formula. And as far as calculations go, that was sketchy for some people when you did all those steps and you had to convert to moles and all of that. Right now, what I want you to know about empirical and molecular formulas. Empirical formulas are your lowest ratio of subscripts, meaning if you look at the little numbers, they're reduced as far as you can go. For molecular formulas, they're not. So they would be things like a 2 and a 4, a 3, a 6, and another 3. They'd be numbers that you can reduce. So if you want to pause and try these on your own, we have a practice where you're identifying as empirical or molecular, and a practice where you're reducing ones that are already molecular. So if you want to pause, you can. Let's see what we got here. My first one's C2H6. I can reduce that. I could divide by 2. So that one is molecular. CH4, low as it goes, empirical. N2O5 and CO2, both of those are also already reduced. N2O5 and CO2 are empirical. NaCl, that's 1-to-1, empirical. S2, Cl2, oh, I can reduce that. That one's molecular. C2, H4, O2, divide them by 2. That one reduces, molecular. BaCl2 is empirical. You can't reduce any further. So for my practice, hey look, it's glucose, everybody's friend, C6H12O6. I can reduce that. I could divide each of those subscripts in that molecular formula by 2 and get CH2O. If you ever take organic chemistry and talk about carbohydrates, which are sugars, they all reduce to CH2O if it's just one ring. So that's nice. I like that one. N2O4, divide by 2. NO2 for my empirical formula. And C3H6, divide through by 3 for CH2 for my empirical formula. Not bad. We will not do the calculations, but that's what's going to be important, is telling if something is empirical or molecular, and then if it is molecular, reducing to its empirical or reduced formula. We did this a couple times. I felt like when I didn't know what else to do, I gave you the mini quiz on counting subatomic particles. We counted them so much. And they come right from the periodic table, from the atomic number, which is your whole number where an element's found, hydrogen's 1, helium's 2, lithium's 3, etc., and your mass number, which we talked about in the first review, which is the decimal mass, rounded. So, protons, found in the nucleus, positive charge. Electrons orbit the nucleus, that's the next packet, negative charge. And a neutron is in the nucleus with no charge. So if you're counting these, and that's what I'm looking at. I mean, I could ask you the trivia like, what subatomic particle is negatively charged? And you're like, electron. We could do that. Also for neutrons, isotopes. All you have to know for isotopes is that it's why the masses are decimals, and that isotopes differ in number of neutrons. So if something has a whole number mass, there's only one isotope. If something has a decimal mass, you got a couple options for your numbers of neutrons in it. That's all with those. So when I'm counting protons, neutrons, and electrons, and I'll get up and erase and show you these examples, my protons and electrons are equal if there's not a plus or a minus, if there's not a charge, and these there aren't. So for these, protons equal electrons, and these equal the atomic number, where I find them on the periodic table. Neutrons are tougher, well, tougher, we have to calculate them. Get your mass number, that's the mass, rounded, and subtract the atomic number from it. So you're going to have a little bit of math to do. If you want to do these on your own for protons, neutrons, and electrons here, go for it. If not, I'm going to erase this trusty board and go for it here. We'll get at least some space. There we go. For, I think we're set up as protons, neutrons, electrons. I deliberately separated protons and electrons even though they're the same. So you had to think about it. All right, there we go. We've got bromine, we've got lithium, and because of my wonderful fish, we've got cobalt. So the first thing I do is I go to the periodic table and I find these elements. Bromine is number 35. Its atomic number is 35. That means 35 protons and 35 electrons. The mass of bromine, 79.906, I think 908. Something like that. It rounds to 80. It's 79.9 stuff. So I would say that to calculate my neutrons, I want my mass number of 80 minus my atomic number of 35, which I believe 35, it looks like 45 to me. So I have 45 neutrons in bromine. Mass number minus atomic number. For lithium, it's number 3. So 3 protons, 3 electrons matches the atomic number. The mass is 6.941. And we've got, so 7, because it rounds up, minus 3, for 4 neutrons in lithium. Almost done. Cobalt, like my little fishy. It's 58.9 something for the mass number. So I know that one. And cobalt is number 27. He's the 6th fish I've had, but he's the periodic table says cobalt's 27. So let's go with that. 27 protons, 27 electrons. 58.9 stuff for the mass, so 59 for my mass number, minus 27, looks like 32 to me. 32 neutrons. Neutrons are the ones that you calculate. Neutrons are the ones that change when isotopes change. Proton equals electron equals atomic number, as long as I don't have pluses or minuses there. We are coming back to those. We are going to talk about counting subatomic particles and ions later, and what that charge does. It only affects our number of electrons, but that's not for right now. So what you guys need to do is finish the review on the back of this packet and double check that you know everything for the quiz that's coming up soon on units 1 and 2. 20 multiple choice. Let me know if you have any questions. Have a great day.